optical time domain reflectometry or the backscatter measurement method. So first of all, we have a fiber, long length of fiber, and this part is the optical time domain reflectometer, through which we can measure the using backscatter method. We measure different parameters associated with the optical link. Let us see how. First of all, we have a pulse laser that will produce a pulse with very short duration, and it is directly going to the fiber, right? And a portion of that pulse will be reflected back in this direction, backward direction, and that reflected part may be coupled using this type of mirror, or this device is also called the coupler, right? So backscattered signal will coming through this port of the coupler, and we have a photodetector, APD type of photodetector. Then we have integrator, log amplifier, and chart recorder to determine the reflected value with respect to the time that can be calibrated in terms of distance. Okay, a light pulse is launched into the fiber in the forward direction from an injection laser using either a directional coupler or a system of external lenses with a beam splitter. Usually only in the laboratory purpose we use a beam splitter. A backscattered light is detected using an avalanche photodetector, uh, which drives an integrator in order to improve the received signal to noise ratio by giving an arithmetic average over a number of measurements taken at one point within the fiber. This is necessary as the received optical signal power from a particular point along the fiber length is at a very low level compared with the forward power at that point by some 45 to 60 dB, and is also swamped with the noise. The signal from integrator is fed through a logarithmic amplifier, and averaged measurements of for successive points within the fiber are plotted on a chart recorder. This provides location dependent attenuation values which give an overall picture of optical loss down the link. So this is one example of such chart, like light pulse launched into the fiber right here. So we have a very large uh, pulse right here. Then the backscatter started. So from the test fiber, this is the test fiber. So backscatter started and the amplitude used to fall. Okay. Then we have a splice or joint. So because of this joint, we have some extra reflection from the joint. So we will get a small spike right here. Okay. Then again the usual backscatter will is shown. Then we have some kind of faulty region with high attenuation, and because of this faulty region with high attenuation, there will be some fault loss like this. So suddenly the slope will change, right? Slope will change, and then again it will start with conventional slope, right? So this indicates the fault loss, and at the end of the fiber we have Fresnel end reflection. So we have a large reflection at the end of the fiber. So once we get this large reflection, we come to know that we have reached the end of the fiber. So by observing the nature of these spikes, the nature of this slope, we can determine uh, different kind of parameters or different kind of problems or faults uh, present in the fiber. Without going to that particular location, we can easily determine the distance from this end, distance of that particular fault from this end. So total characteristics of the fiber is known at the transmitter end only. We don't have to go throughout the length of the fiber to determine where the fault is. So that's the biggest advantage of optical fiber as per maintenance is concerned. This is an example of optical time domain reflectometer. So just picture is shown, but uh, we have we have to connect the optical fiber, and we have to start the machine, and everything will be done inside the all of every components that was shown in the optical fiber uh, backscatter reflectometry um, is present right here, and the chart that we used to see in our previous slide is available and in the screen of this particular measuring instrument. So from that we can easily determine what type of fault is present in the fiber.